everybody doing today? Got some coffee in you? So my main focus for today is to just talk about some fun geospatial stuff and how we're working on a particular project at Fidelity, and sort of stumbled onto the Level Down ecosystem. Most people are familiar with Level Up and LevelDB. Level Down is a suite of alternative implementations, so ranging from flat files to MySQL, DynamoDB, and pretty much everything in between, also in the browser. So a lot of great work done by Rod Vag, Dominic Tarr, etc. So as a consumer, I just sort of looked at some of these things and said, okay, how can I tweak these things, applying some of my experience in the enterprise and how to get sort of clunky things like MySQL to scale. So I'm going to be a little unconventional today, so let's get started. This is my little slide program. You see the help? Let's see if this works. So here we go. Hello, everybody. Next slide. I was going to use prompt so that I could just hit enter every time, but you don't have enough time. So disclaimer: there'll be no furry animals or unicorns or people in bikinis, because there will be no pictures. I didn't have time to get that to work. Yeah. So yeah, like I said before, this is about production level up. We'll take some time to actually see how this little thing is put together as well. Keep it highly educational. So a little bit about my background. I've been coding for a really long time, since I was a kid. My chess coach took me to my first computer science fair, or computer fair, and I put together a 386 with a screwdriver and managed not to short it out because I was doing it totally wrong on the rug. But anyway, had a lot of fun with many languages, and I'm really excited about JavaScript. Before getting into Node, I was sort of your standard enterprise Java guy, and I barely did bad jQuery, but I started on a project called FidSafe, and they wanted to basically create a virtual safe deposit box, and it forced me to kind of look at some alternatives. We were originally implemented Python, and I said, oh, what the heck, this community is growing fast, and I knew just from the old Java days in the late 90s and early 2000s that basically a lot of community and velocity is going to take you really far, and Java, I'm really excited about a lot of you young guys and stuff, selling companies already and things like that actually happened in the Java days too, so it's like just comes full circle. And so, but I think JavaScript has a long way to go, and probably is going to have a lot more knowledge than some of the other sort of classical languages, especially ones you find in enterprise. I kind of look at JavaScript as like an old school gangster. It's like, I'm here and I never left, So what we were tasked to do is basically come up with a geospatial solution. There's a database called Dun & Bradstreet. You can sort of buy that, and you can search for all kinds of different information about companies and who owns what company, if it's public or not, and things like that. So we just had a fairly small data set that we wanted to index and see if we could do something. See if we could do something fun with it. We kind of threw it into the usual suspects, like a CouchDB implementation and a couple other things. But we said the data set's so small. Let's see if we can't use something like LevelDB and just sort of host it for free and stuff. So we started looking at some of the alternative backends and things. Most people know what LevelDB is, so I'm not going to spend too much time talking about it. The main thing is it's a simple key value store with with puts and deletes. And the other cool thing is that it's like graphically ordered, so you can do range sorts and stuff, searches and stuff like that. And snappy compression is a feature, though it's not that big a deal. Level up is basically the JavaScript interface to the primary level. Actually, level up is the top level ecosystem. The whole level up community is kind of bifurcated with like sort of functionality up top, usually creating inverted indexes like for full text search and things like that. And then at the bottom is just basically the storage engines. And so level down is the proper wrapper around level DB. But there's also abstract level down, and then there are sort of level down implementations don't even use abstract level down at all. You're probably going to learn more about this stuff if you go to the workshop that Dominic's going to do later today. I know I'm going to go there. So some of the issues that we faced with our sort of geospatial hack that was that the import process was slow. Of course, there was like no horizontal scalability whatsoever because it's just a single directory. LevelDB creates it has a log, basically merges 2 megabyte files of ordered keys as it grows, and it'll actually compact that as it goes. But it doesn't scale. It doesn't necessarily scale horizontally, and that's something that we were interested in doing so that we could improve concurrency. Because it's not multi-threaded as well. So we looked at a couple of implementations, and they also sort of had naive implementations. SQL Down was one of them. It actually religiously tried to implement the compaction process in LevelDB, and that's like a total waste of time if you're trying to hit like MySQL or Postgres, which have basically upserts built in. So if you're on MySQL, you just do a insert on duplicate update, and you can basically let the storage engine, NoDB, do its thing. So that was kind of, and then they also did a delete on every write. So for a number of reasons, when we did this import of like 1 million keys, the first thing we said was, okay, this thing wasn't tested on 1 million keys. So, and then we started looking for answers. Like it actually took us like a day because we kept on focusing on the writes. We kept on focusing on the writes, and we kept on focusing on the writes. And just the compaction function was running like every 25 writes. It was just happening over here, and the database was grind to a halt. Let's see. I forget which word I was on. Okay. So we did some optimizations to level geospatial. We added a bulk mood for importing data into the database, and we also did the upsert work as I said before. So I think I did skip a slide. I wanted to find, is it 11? Oh, here we go. So this is what was happening before in SQL Down, where it was basically trying to, because of that whole compaction thing, actually because they didn't have support for like updates. So he's gonna look for the old key, try to delete that, and then write it over again. And it's kind of a waste to be doing a delete while you're writing. So it's like 2 steps. This is literally 2 steps forward, 1 step back. So put delete. Let's see. So here's our code now. It's just 2 clean puts, and we actually batch this in an in-memory queue. You can set that size is configurable. That size is configurable, so we set like 5,000. So what it'll do is these writes will happen really fast and synchronously, fill up that 5 5K buffer, and then we also have two flags that we added. We added a 5K buffer. We added a buffer size flag, and we also added a buffer delay flag. So with the buffer delay flag, you can you get two. You can set it to like 2 seconds. So every 2 seconds it'll flush, or if it hits 5K, whichever one comes first. Yep. So yeah, we talked about that. So you know, you might say, well, level down's pretty fast, or level DB is pretty fast by itself. You know, why would you want to use MySQL? Well, the thing is, at least in this naive implementation, you only get you're pegged to one core, and so eventually you won't be able to maximize like I/O on sort of modern boxes. So you know, at Amazon you can get this, these sort of big SSDs and 26 cores and things like that, and you won't be able to leverage any of it if you're kind of just using level DB by itself. So that's why for applications which are like, this is like primarily a read application, it's part of a larger suite of services. It's actually this is a microservice in itself, and all it does is just answer questions about location and companies. And I'm gonna get to that in a second. So the other thing that we did is there was some, because of the way that they were sort of religiously, SQL Down was religiously implementing the write structure, it had to do a subquery to find the max auto-incrementing index for a given key. And so when we just did the upserts, that got rid of that. And so that was a sort of massive performance improvement. Almost done with these slides. We get to some more fun stuff. So what were the results? So just level DB by itself, not really tuned on sort of crappy hardware in our internal cloud. We were getting 800 inserts per second. So one thing about benchmarks, people are like, oh, 805 inserts per second. Well, most people think that's either pretty sucky or pretty good, depending on your state of mind. Remember, this is one box. And also, we're not just doing like these little tiny keys and these little tiny values. It's actually like a substantial payload. And actually, the other thing to think about is that this insert number is for the actual rows. So the actual transactions per second is double that, because we are actually doing 2 writes for every row that's actually recorded in our benchmarks. So for all of these numbers, you can double that for the actual raw TPS. So just on simple, in a VM rotational disk, 1,600 transactions per second. So, and then you get into the old MySQL land. Basically, this is a little shy of 100 transactions per second with just naive inserts, auto commit, that sort of dumb stuff. So once we got into doing sort of bulk transactions, started seeing improved performance, 300 plus. Then for this one, we actually, begin the transaction, and then we stream in the inserts on duplicate updates, and that's we're getting close to 800 transactions per second, and then for one last thing, we said, well, if you're starting with a fresh database, and the thing is that we get these file dumps like every month, and we have to basically import them while keeping the service up and running. So we preferably would want to just stream into a clean database, instead of doing the updates, though we support that because we're trying to build this so that people can just say, oh, well, I have a lot of MySQL, and just pull our level MySQL off the shelf and just use it, and know that it sort of has this sort of like old school best practices if you want to use MySQL as opposed to something else baked in. Don't worry, this is not all about MySQL. Okay, so that's all for this section, and you can find level MySQL, which is sort of a fork of SQL down. It's been stripped down to only support MySQL, and it's optimized for MySQL. You can find it here. So now I want to talk about probably something more interesting, because I know a lot of you guys are doing, startups and things at web scale, and this was like focused on web scale. This is focused on more just a microservice, a read-only microservice. But how would you, use level geospatial and actually get it to work on, like, say, Internet of Things or something like that? So for that, I want to first show you. There we go. So this is our headquarters. That's a lat long for it, and this is the quad key. So for level geospatial, they use a quad tree, and that's something that was actually it's old science, like but Bing uses it. So Bing, for their tiles, they use it, and so how it works is basically. What a quad key actually is it's a single dimensional index that encodes X and Y positions as you traverse the string. And so at every position in the string, it encodes a particular level. That value can be 0, 1, 2, or 3. And that encodes, and that will either encode no additional information, just latitude information, or lat long information. And so this is what it conceptually looks like at every level. And just for the curious, and as you see as the levels increase, the lengths of the string grow. But you'll notice that as you go back to a parent, a level up, that the keys are shared. And that's going to be really important when we talk about how we can scale this to more sexy databases like RethinkDB and, dare I say, DynamoDB. So remember that that's our particular location, and that's a fully encoded 22 levels. Let me look at my help. Okay, precision. I'll show a quick demo after this. So this is a quick look at what how the precision affects the length of the quad key. No, this is it. That's the farmost left column. Oh, sorry. All right, does that help? Yeah, so that's the precision, and as the precision increases, the length of that key increases, and that's going to be important in a second. So let me get to the, I believe this is radius. All right, so this is the fun table. So it kind of breaks down how the radius impacts the precision based on like what kind of search you're going to do. So this is a single point, obviously, and that's the full encoded path. The minimum distance that you can start encoding at is 4 meters, Everything else like returns like infinites and like zero bars, nans and stuff like that. Not good. Our search is kind of optimized for a kilometer, and so we encode. So we could potentially use a precision of 13 as a hash key. I'm going to speed this up because I'm running out of time. And also, I encode in here a couple other things. So if you look down here, it's like a 3-hour drive, 321 kilometers or 200 miles is 5. And that's interesting because, like, say if you were running a dating service and you wanted to implement, like we all know because we've been here for the whole week, you want to implement a microservice for just your location stuff. You might want to encode a prefix of just 5 characters, and you could use that as a partition key. That's basically where I'm going with this. And so if you go, in our case, for our data stored in DynamoDB, just going to show you what this looks like. Come on. Going to do 2 more things, and then I'm going to cut out because I don't want to keep you guys from your food. So one of the optimizations that we did for Dynamo Down. So Dynamo Down is another implementation, runs against DynamoDB, Amazon's massively scalable SSD-backed database. The problem was they were stuffing. If you wanted to use Dynamo Down, they were going to stuff the whole range key inside a single key. Actually, they just used an arbitrary key. And then stuffed all the data. So it didn't matter if you had 2 megs or a petabyte. If you use Dynamo Down, it's all going to stuff it in one key, which does not scale on DynamoDB, which actually represents probably a single MySQL server behind the covers. So what we do is, for our needs, every month we get a new file. So we start with this. We prepend. We add a level, a precision of, I think, 10 here. And that way 10 pretty much represents, I think, 6 miles. And so every 6 mile blocks, that we sort of gracefully partition our data across Dynamo. But actually, if you were using something like RethinkDB, you could use this as the partition key as well. And so this just shows you what that data looks like. You'll see that these things are paired. So you see the 2 puts. One is for actually doing direct key lookup by UUID, and one is by looking up the information by the actual quad key. Let's just take a quick look at it in action. I'm gonna show you how this is running against Dynamo, and you'll see. We can slide this is impacted by the crappy network a little bit. You'll see like the return. Let me see if this comes back. When this updates, it'll actually show the time it takes. But I can actually. I'm going to quit here, go down. Because of the crappy network, the time that it takes to do everything on the application server and then the time that it takes to load all the information to the browser is actually skewed. But I just want to show you one thing, if it's actually here. Oh, it's loading. Thank you, Amazon. All right, this is the only number. This is like end of the presentation. Like this is the only number you need to care about. How long do those queries take? Now, when you do a query, I'll just explain this one last piece, and then you can get to your lunch. But the way it works is when you get a particular location and a radius, like I'm searching for all guys who are single with no children, whatever, in this particular radius, right? So you start with the lat long. That gets encoded to a full 22 a 22 length quad key, right? And then what happens is, based on how many blocks are actually in the radius from like the top right to the bottom left, it'll subtract from that full 22 to get down to the prefix, right? And then the prefixes are segmented into this block, this block, this block, and this block about that centroid. And then 4 searches are done to grab all of the information. Like, so this is a block. And remember that all that information in that block is encoded as a one-dimensional key. So within that block, it'll do a quick search through. So for every query that you basically do for location, using a quad key or geohashing in general, you're going to do four actual queries. You'll see that the query latency in milliseconds is 20 milliseconds for all the queries that we've been basically doing in these demos and stuff like that. If I run siege against this, you'll see that you'll see that even though we might get horrible numbers, so we're getting like 1 second, 2 second, but that's more has to do with the network latency here. But when we go back to Amazon, we'll see that query latency is still low. So if you're properly load balanced in your data center at your app tier level, and if your customers actually have good Wi-Fi, they should be seeing the results no problem. And so if we go back here, you'll see that is still just fine. Last thing, yeah, there it is. It's just updated. That little last tick is actually much faster. And just the last thing I want to show is, oops, get here. Come on. This is just the presentation itself. So using some fun stuff, nom nom, and that's it. Yep, that's it. Thank you.